Welcome to Automated Visual Software Analytics. This part is about execution tracing. In this part, we will introduce principles of execution tracing. We will discuss traces and call graphs, and we will explain several aspects of logging system behavior. Let's start with principles of execution traces. This is the overall picture where execution tracing is applied within software analytics. We would like to extract data about execution of software systems by tracing the dynamics of a system, recorded by traces, and this forms part of the general database that is used by software analytics later on to visualize aspects, to correlate information, and, for example, to generate software maps. It's an important aspect because behavior is one central and key dimension in comprehending software systems, especially if they become complex. Let's see how we can define execution tracing. Execution tracing is a general form of logging information about the execution of a software system during its execution. So we do not model the behavior and we do not reconstruct behavior. We would like to record the behavior, to record every instruction that is executed during runtime, that is, during a special run of a software system, for example, applying test cases. Characteristics. Execution tracing captures the actual system behavior, not the modeled system behavior and not the default system behavior. It captures the actual system behavior. Execution traces, this reveal what the system was doing while it was executed for the underlying finite captured system run. The system run is always finite and it's captured. Maybe it takes 1 second, 1 minute, or 1 hour, or even 1 day. The granularity of recorded behavior depends on the applied execution tracing technique. For example, we could apply full code instrumentation or only partially log certain system functions we are interested in. So the granularity is one key parameter of execution traces. What else can we tell about execution tracing? The characteristics. Execution tracing analysis, if we analyze recorded data, is key to a number of tasks in software analytics. For example, we can investigate the system behavior based on these samples of system execution. We can foremost localize errors or other functional deficiencies. This is a key application, looking back what happened and why did it get wrong. We can understand interaction of system functions, components, and subsystems, especially if they are complex ones. We can understand interaction between several threads. So for multi-threading, it's also a key technique to understand what the system is doing when it is executing. We can understand control flows, and we can, this is a more traditional use of execution tracing, we can compute test coverage and, of course, profiling information about the performance of a software system. In that sense, execution tracing is a general purpose means for software quality measurements and analysis, because it reveals a lot of key information about the actual system behavior. And for that reason, it is also a general source of information that is used by software analytics. Now let's go on to define trace and call graph as well as control flow. Control flow is the underlying concept that we will investigate by means of execution tracing. A control flow in general denotes a sequence in which operations are performed during the execution of a computer program. Sometimes control flows are modeled in advance during the design of a software system, for example by unified modeling language sequence diagrams. But we are interested in the actual control flows a system shows when it is executed. Understanding the actual control flow is very important because by execution tracing we can get behavior information that can be used to understand the control flow of modules based on and limited to, of course, to the sample system runs. So the test cases we apply when we execute the system, of course, define the borders in which we can actually record system behavior. So a good choice of test cases is very important. Yeah, the knowledge of the control flow is essential for most software maintenance tasks and hence has an enormous impact on software development effectiveness and behavioral analysis. Especially for software maintenance, understanding control flows are essential because this is a key part in program comprehension. So, based on control flows, let's have a look on the next key concept. It's a trace. A trace is a record of the execution of a computer program that contains all or selected function calls performed and optionally the value of parameters passed to the function or returned by the function. So by trace we mean one record that contains a number of executed functions and their parameters and return values. Yeah, based on that we can now construct call graphs. A call graph is a hierarchical abstract representation of a sequence of functions called during the execution of a system. The graph's nodes correspond to functions or other entities being called modules, black box calls, and calls are represented by edges between these nodes. Call graphs with a low number of nodes and edges can be depicted, of course, by classical node-edge diagrams or graphs. For example, below you find such a big call graph represented by a diagram, and what we also see is that we do not see anything because there are too many nodes, too many edges, so most likely it's not a good representation. For that reason, we have to ask how can we efficiently visualize execution data. In this example, we have a call graph, a formal call graph, nodes that represent functions. This is a function f in this little example, and it's calling g and h several times, and finally optionally k is called. And if according to the test data filled in, we get different call graphs because we have different control flows in the system. And yeah, both examples are traces, so we have two traces. We have two call graphs, and we can now better comprehend the control flow of this little example. The trace data, interestingly, has to record at a certain granularity the functions called. In this example, we decided to denote only we decided to record only the functions as explained on the right. So in the first example, f with parameter 2, we get these trace data entries, the entering in a function and the exit of a function is explicitly recorded, and parameters are recorded as well. This is still an abstract representation of trace data, also for the second use case, it's a little bit longer. And what we can see is that trace data tends to become large if we record system behavior at a low level of granularity. Or a high level of granularity. In this case, that means many details are included. So we have to find ways to compress this data as well. Now, let's have a look at different aspects of logging system behavior. If we log system behavior by trace data, then we will find out that program runs recorded, the underlying data gets extremely large in terms of recorded statements and, of course, corresponding storage requirements. Even runs of a few seconds can generate hundreds of millions of trace data entries, depending on the detail level at which tracing takes place. The execution of recursive and iterative algorithms, for example, leads to almost an explosion of entries in recorded traces if they are mapped in an unfolded way, that is, if they are not compressed or further abstracted. Execution trace data also needs to be filtered in general, and it has to be abstracted or generalized. For example, this means that calls to standard library functions or other black box modules can be pruned, cut off, because sometimes we are not interested in, because we trust that these functions are implemented well. At least we don't want to have a look inside these functions or modules. If so, we can prune them. We can also compress iterative and recursive calls by automatically detecting such situations based on the given trace data. For example, we can look for patterns that indicate recursion or patterns that indicate iteration, and then we can fold maybe some hundreds or even thousands of data entries into one single, more abstract entry inside a trace. Yeah, the limitations that are inherent to logging system behavior by execution traces are the following. Execution tracing can have a varying degree of performance decrease depending on the code instrumentation technique that is used. Performance decrease can be a crucial factor if, for example, real-time behavior of an application changes. There's another limitation: getting programs, systems that do tracing, that enable tracing. It's sometimes difficult to get such variants of the application on a customer machine, because it depends on the customer's willingness to install the tracing-enabled version and on the willingness to hand over the trace data at the end of the execution. This might be caused because execution trace data can include sensitive information about a product's source code, because parameters are traced and function names are recorded, or sensitive information about customer data, for example, amounts of money or personal data. So sometimes it's difficult to get trace data from customers, from the customer side, from the deployment at the customer site, if sensitive information is included. Then in this case, sometimes it helps to abstract this information or to aggregate that information, or in any way to mask that sensitive information. The information value of trace data depends also on the correlation of execution path at runtime and the system use cases of interest. So a good choice of use cases is essential. Otherwise, we do not get to these parts of the system that are really interesting, for example, because they are tricky or they are error-prone. So a good choice of use cases is also very essential if we apply execution tracing to log system behavior. Yeah, let's summarize this part. We have learned that execution tracing is a fundamental and a very powerful method to log system behavior while executing the system to get the actual system behavior. The recorded trace data is a basis for system behavior analysis. For example, the data serves to reconstruct partially control flow graphs or to compute test coverage. Execution trace data can store, depending on the tracing technique used, detailed or less detailed information of the sequence of instructions executed, including function name, time of entry, time of exit, values of parameter, values of variables, global variables, for example, and of course returned values of functions. Yeah, logging system behavior by its nature generates large data sets because within milliseconds, 100,000 of instructions are typically executed by a complex application. They are not suited to be inspected manually in comparison to tracing used in debugging, which relies on a manual step-by-step inspection, step over, step in. Execution trace data are supposed to be analyzed, evaluated, and visualized by means of visual software analytics. This is the content of the part about execution trace views. So in software analytics, we take advantage of the detailed information in trace data and to correlate that data with other aspects of the system and to map it in a more abstract way, in a more understandable way, for example, by software maps. Yeah, this concludes this part about execution tracing. Let's have a look at the terminology introduced. Execution tracing is a general form of logging information about the execution of a software system during its execution. A trace is a record of the execution of a computer program that contains all selected function calls performed and optionally the value of parameters passed to and returned by each function. We also introduced the term control flow. A control flow denotes a sequence in which operations are performed during the execution of a computer program, and call graph, a formal representation of the calling sequence of a computer program, whereby a node of a call graph represents a function, an edge represents the invocation of a function call. That is, it defines a call-callee relationship. As further reading, I can recommend this article about Towards Introducing Execution Tracing to Software Product Quality Framework. So there's indicated that execution tracing is a key information to better handle and manage software quality. It's an essential aspect that is used to measure, to observe, to monitor software quality. Yeah, let me end with some remarks about execution tracing. It's a well-suited and essential instrument to analyze behavior of especially distributed systems, multi-threaded systems, and embedded applications. Especially in these three cases, there's almost no chance to understand their real control flows, their actual system behavior, by means of static analysis or by means of object-oriented modeling or by other formal methods. The actual system behavior can be reconstructed very efficiently by execution traces for these three types of applications. Execution tracing for a representative collection of tests provides key information about performance aspects, especially used by profiling tools, but also about code coverage, so key aspects in software quality. It can even be used to analyze specific software properties, such as energy consumption, for example. For mobile application, it's important to know where is the system really executed and what about the energy requirements that are behind. To gain insights into execution trace data, the data has to be post-processed by filtering all irrelevant parts. For example, these calls to functions that are not of interest, black boxes or standard library calls. By compressing technical sequences of trace entities, for example, we can skip or compress or fold operator resolution calls, type conversion calls, etc. And we can also generalize highly repeated calls due to iterations or recursive algorithms. Data mining is used typically on trace data to do this. Execution, tracing, and other logging functionality represent an important and commonly found part of the functionality of any complex software system. Interestingly, even large parts of the source code of a complex software system deals with execution tracing in a certain way. For example, we will find in typical systems you can find logging code, constraints or parameter checkings, assertions, or other forms of capturing and reporting runtime behavior aspects. So sometimes, and in most complex systems, logging functionality is also part of the whole software system itself. And execution tracing and logging functionality are typically not fully included in product versions of the software system due to performance aspects, because the execution tracing always implies a certain performance decrease. So sometimes it's turned off or partially or fully disabled for the product version of a software system or application.